Hey, welcome to engineeringtalks.com. In this video, we'll go through the stress and strain variations along the depth of a beam. The previous two videos were on the topics pure bending or simple bending and theory of simple bending. So you can watch those two videos first in order to have an understanding of what is meant by pure bending or simple bending, what are the assumptions made in the theory of simple bending, and finally the theory of simple bending. We also went through the definitions of neutral layer or neutral surface as well as the neutral axis. I also explained in detail regarding the tensile stresses and compressive stresses acting in the layers depending upon their position with respect to the neutral layer. So please do watch those videos in order to have an insight into these topics. Here I have shown a part of a beam which is subjected to simple bending. Consider a small length delta x of this part of the beam. Let AB and CD be the two sections perpendicular to the axis of the beam. Let NN be the neutral layer or the neutral surface and PQ be a layer which is situated at a distance of y meters below the neutral layer. This figure shows the part of a beam after being subjected to bending. So here you can see that the topmost layer AC has been shortened to A prime C prime, whereas the bottommost layer BD has been elongated to B prime D prime. The layer PQ has also been elongated to P prime Q prime. We know that the length of the neutral layer before and after the bending remains the same. So NN is equal to N prime, which is equal to delta X. The length of the neutral layer remains unchanged. So, before the bending takes place, the lengths of all the layers in between the sections AB and CD will remain equal to delta X. See, look here. Length of AC is equal to length of NN is equal to length of PQ is equal to length of BD is equal to length of all the layers in between the sections AB and CD. This figure shows the condition of the beam after the bending takes place. Here you can see that some of the layers have been shortened while the others have been elongated. Only the length of the neutral layer Nn remains unchanged. That is Nn is equal to N prime which is equal to delta X. Now if we extend A prime B prime and C prime D prime, it will meet at O. Let theta be the angle subtended at O and let R be the distance between this point O and the neutral layer N prime, where R is the radius of the curvature. Here you can also see that the layers situated above the neutral layer have been shortened, whereas the layers situated below the neutral layer have been elongated. So the layers above the neutral layer will be subjected to compressive stresses, whereas the layers below the neutral layer will be subjected to tensile stresses. Now let's look at the strain variation along the depth of the beam. Before bending of the beam, the lengths of all the layers in between the sections AB and CD will be equal to delta X. So before bending, NN is equal to delta X is equal to PQ. After the bending, we can see that the layers above the neutral layer have been shortened, whereas the layers below the neutral layer have been elongated. But the neutral layer, the length of the neutral layer remains unchanged before and after the bending. So Nn will be equal to N prime will be equal to delta X. Since PQ has been elongated to P prime Q prime, the length of P prime Q prime will not be equal to that of PQ. Now from this figure we can get the length of the arc N prime, right? So length of N prime will be equal to R into theta. But N prime is also equal to Nn, which is equal to delta X. So delta X is equal to R theta. So we can write PQ is equal to delta X equal to R theta, since PQ equal to delta X. Now we have to find out the length of P prime Q prime. So the length of this arc P prime Q prime will be equal to r plus y into theta, as it is located at a distance of y meters below the neutral layer. So P prime Q prime is equal to r plus y into theta. Therefore, the increase in the length of the layer PQ will be equal to P prime Q prime minus PQ, which is equal to r plus y into theta minus r theta, which is equal to r theta plus y theta minus r theta, which is equal to y theta. Hence, strain in the layer PQ will be equal to increase in the length of the layer PQ by the original length of the layer PQ. So, y theta by r theta, which is equal to y by r. So, here you can see that the strain is directly proportional to the distance y. So, the distance y is the distance of that particular layer from the neutral layer. Hence, the strain in any layer is proportional to the distance of that particular layer from the neutral layer. Let's look at the stress variation now. Let sigma be the stress in the layer PQ and E be the modulus of elasticity or Young's modulus of the beam. We know that Young's modulus E is equal to stress by strain. So here E is equal to stress in the layer PQ by strain in the layer PQ. We already found out the strain in the layer PQ, right? It is equal to Y by R. So on substituting, we get E is equal to sigma by Y by R. Therefore, stress sigma is equal to E by R into Y. E by R is constant. So sigma is directly proportional to Y. Hence, stress in any layer is proportional to the distance of that particular layer from the neutral layer. This equation can also be written as sigma by y is equal to E by R. Please do like and share the video and subscribe the channel. Thank you.